In today's lecture, we are going to see the inelastic photon-phonon interaction. When you say inelastic photon-phonon interaction, that means the inelastic scattering of photon by phonon. This is the subject matter of our today's lecture. Actually, you have studied Bragg's diffraction or Bragg's reflection earlier in very detail, and you have seen that when electromagnetic radiation is incident on a crystal and the interaction of the electromagnetic radiation with the crystal is elastic, then Bragg's reflection takes place. When you say Bragg's reflection, that actually means Bragg's diffraction, but Bragg has used the term reflection. And in this elastic scattering of EM wave, or you can say the elastic scattering of photon, there is neither a creation nor a destruction or absorption of phonon. It means when Bragg's reflection takes place, no phonon is created or no phonon is absorbed. Okay? But what will happen when the scattering is not elastic but it is inelastic? Okay? Actually, it is found that in case of inelastic interaction or inelastic scattering, there is either a creation of a phonon or an absorption of a phonon. It means a phonon may be created or may be destroyed or may be distracted or may be absorbed in case of inelastic scattering. So when you made the electromagnetic wave to be incident on a crystal, and this interaction of the electromagnetic radiation, that is photon, with the crystal is inelastic, then definitely there will be either a creation of phonon or destruction of phonon. Okay? So let us now see what's the cause behind this. Why this phonon is either created or absorbed when inelastic scattering takes place. What is the actual reason behind this? Actually, the photon-phonon interaction mainly occurs due to the change in the local concentration of atoms. And when the local concentration of atoms changes, then actually refractive index of the crystal gets changed. And due to the change in refractive index of the crystal, the speed of the mechanical wave or the acoustic wave generated will also change. Okay? And the speed of the electromagnetic wave passing through the crystal will also change. So actually there will be some mechanical disturbance due to this variation or change in refractive index, which is led by the local concentration of atoms. Okay? And that's why this photon-phonon interaction occurs. Okay? Actually, the cause may be also thought in terms of the wave aspect or wave nature of the electromagnetic radiation. You know, in electromagnetic radiation there are two field vectors, the electric field vector and the magnetic field vector, but electric field vector is very strong in comparison to the magnetic field. So whenever we deal with the problem of interaction of electromagnetic wave with any other thing, then we think about the electric field. So actually the electric field vector of the EM wave or the light wave induces a mechanical vibration in the medium. Okay? And this mechanical vibrations actually affects the elastic properties. Okay, and that's why this photo, photon and phonon interaction actually takes place. Okay, actually now our aim is to find what will be the frequency or the wave vector or the wave number of the produced photon or absorbed photon. Here I am just going to see the inelastic scattering in case of which there will be a creation of phonon. We are going to see that. Okay? And for this, let us consider there is a crystal. Let us see this is a specimen of crystal. And we incident an electromagnetic radiation to be incident on it. This is your crystal, and on this crystal an EM wave is incident. EM wave. Okay? And you know the quanta of EM wave is photon. So you can also say that a photon is passing through this crystal. Okay, and we also assume that this crystal has refractive index n, and this n is constant. We assume it. Okay, and the photon which strikes this crystal has a frequency nu, which is equal to omega ph divided by 2 pi, where omega ph is the angular frequency of the light wave or the photon. Okay? And we also assume that the wave vector of this incident photon is a kappa hat. Sorry, not hat but kappa. Kappa is the wave vector of this incident photon. We consider it. Okay? Now we know the wave velocity or the phase velocity of a wave v is given by omega over kappa, where omega is the frequency of the wave and kappa is the wave number. Okay, so the wave velocity or the phase velocity of light wave inside this crystal will be what? This will be v equal to omega ph divided by kappa. But you know, v is the velocity of the light wave in the crystal, and if c is its velocity in free space, then you know v is equal to c over n. Actually n equal to c by v. This is just basic definition of refractive index. Okay, so n is c over v, so v will be equal to c over n. So instead of v, here I have written c over n, and this is omega ph divided by kappa. Okay, and so that you can say this omega ph is equal to c kappa divided by n. Okay, this is the angular frequency of the incident photon or incident light wave. Okay, now you know this omega a will be equal to 2 pi nu, where nu is the regular frequency of this light wave, and this is equal to c over n, and instead of kappa I have written 2 pi over lambda. You know wave vector kappa is equal to 2 pi over lambda. Now this 2 pi and this 2 pi will cancel out, and when you will make here a cross multiplication, you can see this nu times lambda will be equal to c over n. This is actually the well-known formula that v is equal to nu lambda. This is a well-known formula. Okay. Now let us consider that this is the photon which is moving just, let us say, in x direction. Its wave vector is kappa and frequency is omega ph, and this small sphere actually represents the crystal, or you can say this is the scattering center. This is the scattering center. Okay, and when this photon is incident on this scattering center or the crystal. What happens? Actually, the incident photon gets scattered at an angle theta, as you can see in this figure. Actually, this direction which makes an angle theta with the incident direction, that is the direction of a scattered photon. And during this inelastic scattering, the wave vector of the photon is changed to kappa dashed, and its frequency becomes omega dashed ph. Okay? And due to this interaction, a phonon is created, and that phonon recoils in this direction, as you can see, and this is the direction of phonon, moving phonon, and this k is the wave vector, and omega is the angular frequency or cyclic frequency of this phonon. This theta, which is the angle made by the scattered photon with the initial direction or original direction of photon, that is called angle of scattering. So what is this theta? You can see this is called angle of scattering. Okay? Angle of scattering. Now you know, in any scattering process, we can apply or we can use the energy conservation law and the momentum conservation law, because in either in elastic collision or in inelastic collision or scattering, the total energy remains conserved and the total linear momentum also remains conserved. So now let us apply the energy conservation. You can see the total energy before interaction or before scattering will be equal to total energy after scattering. But before scattering, in this colliding system, there is only one thing, and that is the incident photon. But after collision or after interaction, there are two components of the colliding bodies. One is the scattered photon and another is the phonon. So, according to energy conservation principle, the total energy of incident photon will be equal to the sum of the energy of the scattered photon and the phonon. Yes or no? You can see. So according to energy conservation principle, energy of incident photon is equal to energy of a scattered photon plus energy of created phonon. Okay? But what will be the energy of incident photon? You know, the formula for energy of photon is h bar omega. Now, the frequency of incident photon is omega ph, so its energy will be h bar omega ph. And the frequency of a scattered photon, you have assumed omega dashed ph, so its energy is h bar omega dashed ph. Okay? And the energy of the created photon is h bar omega. So, applying the energy conservation principle, you can write the equation like this. This is h bar omega ph equal to h bar omega dashed ph plus h bar omega. Or equivalently, you can also see that this omega ph is equal to omega dashed ph plus omega. And from here you can conclude that the frequency of the incident photon is not equal to, in general, the frequency of the scattered photon. But frequency of the scattered photon is smaller than the frequency of the incident photon. Okay? Now in the similar manner, you can apply the momentum conservation principle or the selection rule for the wave vector. And applying this momentum conservation, you can say that momentum of the incident photon will be equal to momentum of the scattered photon plus momentum of the phonon. And as you know, kappa and kappa hat are the wave vectors of the incident photon and the scattered photon, and k is the wave vector of the created phonon. So momentum of incident photon is h bar kappa, and that of the scattered photon is h bar kappa dashed, and the momentum of the phonon is h bar k. Okay. Again, eliminating h bar, you can write equivalently that kappa is equal to kappa hat plus k. Okay. You can construct a vector triangle just on the basis of this equation number 5. You can see. According to triangle law of addition, if you consider that this point is A, this is B, and this is C, then according to triangle law of addition, you know vector AB plus vector BC will be equal to vector AC. This is in accordance with the triangle law of addition. But here this is kappa hat plus k, and that is equal to kappa. Okay. So this vector construction is in accordance with this equation 5 after applying the vector addition law, that is triangle law of vector addition. Okay. Now from this result you can find the magnitude and direction of this wave vector k of the phonon. But before that, one thing here we should note that during this scattering process, a very small part of energy of the incident photon is lost in the form of phonon. Okay? In the form of phonon. But before that, one thing here I have mentioned, that this equation 4 has been written only by considering the scattering of photon by phonon, neglecting the Bragg's diffraction or Bragg's reflection. It means you can say that this equation 4 has been written without taking the Bragg's diffraction under account. Okay. We have considered only a scattering, and then you have written that equation. Okay. Now you know that if Vs is the velocity of the sound or the phonon, and if it is assumed to be constant, then the velocity Vs, which is actually the velocity of mechanical vibration or phonon or sound, you know this is equal to omega over k. And so omega is Vs into k. But actually this result will be used sometime later. I have but mentioned it here. But what I was telling you just earlier, that in this process, the incident photon loses energy, but the loss of energy by the incident photon is very small. It means the energy of the created photon is much smaller than the energy of the incident photon. So for a time being, in our calculation, we can neglect the energy of the created phonon in comparison to the energy of photon. Okay? So you can say that this h bar omega, which represents the energy of phonon, that is much smaller than the energy of photon. This h bar omega ph is what? This is actually the energy of photon, and this energy of photon is much greater than the energy of phonon. So in our energy conservation equation, or in this equation, you can say we can neglect this h bar omega, and when h bar omega will be neglected, then the result will be simply h bar omega ph is almost equal to h bar omega dash ph. Okay, h bar omega ph is almost equal to h bar omega dash ph, or you can say that omega ph is almost equal to omega dash ph. As you have seen in case of elastic scattering, this omega ph is exactly equal to omega dash ph. But in this case of inelastic scattering too, we can consider that the frequency of the incident photon and the frequency of the scattered photons are almost equal, not exactly but almost equal, because the frequency of the phonon is much smaller in comparison to the frequency of the photon. Actually, in the similar manner, the magnitude of the wave vector of the created phonon is also much smaller than the wave vector of the photon. So in accordance with this equation 5, you can also neglect this k in comparison to kappa. Okay, so when we will neglect it, our result will be simply kappa is almost equal to kappa dashed. It means the magnitude of the wave vector of incident photon and the scattered photon are almost same. Okay, so considering this very fact that kappa and kappa dash, that is the wave vector of incident photon kappa and the magnitude of the wave vector of scattered photon kappa dash are almost same. Taking this very fact under account, now you can find the magnitude of the wave vector of the created phonon. You can see this vector equation. Kappa is equal to kappa dashed plus k. So from here you can write that k is equal to kappa minus kappa dashed, and so that the modulus of k is equal to mod of kappa minus kappa dashed. But you have seen that the angle between this kappa and kappa dashed, angle between these two vectors we have assumed theta, and magnitude of these two vectors are equal. Actually, you have studied in your elementary course on vector algebra that the mod of a minus b, this is 2a sine theta by 2. But if mod of a is equal to mod of b, then this result holds. Here at the place of a there is kappa, and at the place of b there is kappa dashed, and the magnitude of kappa and kappa dashed are almost same, as you can see it here. So utilizing this elementary formula of vector algebra, you can write that modulus of vector k, that is k is equal to 2 kappa times sine theta by 2. Okay, as I have told you earlier that this theta is an angle between kappa and kappa dashed, that is the angle of scattering. So in this way we have obtained the value of the magnitude of the wave vector of the created photon. And you can see this magnitude of wave vector depends on the magnitude of the wave vector of the incident photon and the angle of scattering theta. Okay, angle of scattering theta. On these two factors, the magnitude of the wave vector of the created photon depends on. Okay. So I have written it here. Thus a phonon is produced when a photon is scattered inelastically at an angle theta from the direction of incidence. Okay. Now as I have told you earlier that I have written here this equation earlier. This omega represents the frequency of the created phonon, and now we have obtained the value of k. So substituting the value of k in this equation 6, now you can find what will be the frequency of the produced phonon. As you have seen that this omega is equal to Vs into k, where Vs is the velocity of sound or velocity of phonon in the crystal. Okay, and you have seen that k is equal to this much. So substituting the value of k, you will get omega equal to 2 Vs times kappa times sine theta beta. Okay. Now again you can see this kappa. Kappa can be written from here. See the initial equation. This equation. Equation number 1. From this equation you can find the value of kappa, and that will be equal to what? That will be omega ph into n divided by c. So instead of this kappa, which represents the wave vector, magnitude of wave vector of incident photon, I have written here omega ph into n divided by c. So finally we get that the frequency of the produced phonon is equal to 2 Vs times omega ph into n divided by c into sine theta beta. This is the frequency of the product. Or in other words, you can also say, you have seen that omega ph is equal to omega dashed ph plus omega. Okay, so omega is what? Omega is actually omega ph minus omega dashed ph. So you can also say that this omega is actually the change in frequency of the incident photon. How much how much the frequency of the photon will change, that is represented by this omega. Okay. Actually, this equation 8 has an experimental evidence. It has been experimentally verified indirectly. Actually, when a crystal is taken, particularly the experiment has been performed by taking the quartz crystal, or instead of quartz, the experiment has been also performed for sapphire crystal. Sapphire. And on this crystal, the electromagnetic radiation of the range of microwave, that is incident. Okay, and this microwave is actually obtained or produced by a laser source, and that light is incident on it. Okay, actually in that condition, the observed shift in frequency or observed change in frequency was measured by putting the value of velocity of sound wave, which is measured by ultrasonic method. It is found that the value obtained experimentally fits well in this theoretical expression. Okay. So in this way we can say that this formula has an indirect experimental test. So I have mentioned it here. You can just see the phonons have been generated in quartz or sapphire in the microwave frequency range by scattering the visible light produced from an intense laser source. Okay, and the observed shift in frequency of the photon agrees well with the shift calculated in equation 8 using the velocity of sound determined by the ultrasonic method at low frequency. Okay, so substituting the value of Bs, we can measure omega, and the measured value of omega actually agrees with the value of omega obtained from this result. Okay, so this is all about the inelastic scattering of photon by a phonon. Okay, and I think this discussion was very simple, the calculation was very easy, the equations are very simple. So definitely you have a clear cut concept now, uh, what is called the photon phonon inelastic interaction. Okay, thank you very much.